Thank you, Tom, for the introduction. And this is work that I've done with the Fangfei Liu, Chan Ge, Gernot Heiser, and Ruby Lee. And it is last level cache side channel attack. And if the title sounds very similar to the previous talk, that's no coincidence. We worked independently and found basically the same attack. So we are going to hear some similar things and some different. And so motivation, as we said, is clouds, and clouds, as we know, are not made of droplet of waters. We have virtual machines in clouds, and we have the hypervisor that supposedly keep virtual machines isolated from each other. But because the virtual machines share the same hardware, there is a potential for side channels between them. And this has been known to be a problem problem of side channels has been known for over 10 years, and in recent years we've seen the problem in a virtualization environment. Now, we are interested in last level cache side channel attacks, and the reason is, as Gorka said, the last level cache is shared, so most side channel attacks that applied against the cache in the past were on L1, and then we need either hyperthreading in the core or exploit scheduler weaknesses. And the only last level cache attack, the flash reload, requires memory duplication, and both these are easily mitigated. Clouds tend not to use hyperthreading, and they do not provide shared memory, or page duplication. So our attack does not have these restrictions, and in addition to the previous attack, our attack does not require synchronization between the attacker and the victim. So a bit about cache structure. The hardware cache is a small bank of memory, stores units called lines, and arranges multiple sets. Each of them consists of multiple ways. The number of ways is fixed in each set. And we have the memory, and the memory maps into the cache so that each memory line goes to a cache set. And each memory line can go into to any of the ways of this cache set, but we don't know to which way it will go, but it will go to one of the ways in this specific cache set. Now, this structure has been exploited as a side channel with a prime probe attack, developed incidentally by two different groups independently at the same time. The attack works like that. The attacker chooses a buffer, cache-sized buffer of memory. The attacker then accesses this buffer, so this buffer is now in the cache. The attacker knows what the cache state is. When the victim executes, the victim accesses some memory and replaces memory in the cache. The attacker now can measure the access time to its own buffer, and for cache sets, or for memory lines that reside in cache set that has not been accessed by the victim, the access will be fast because the attacker will get all the information from the cache. For cache lines that come from that the victim has accessed, the access will be slow. So the attacker can distinguish between cache sets that the victim has accessed and cache sets that the victim has not accessed. And from that, the attacker can infer information about what the victim has done. In the 10 years that have passed since these attacks were published, we haven't seen side channel attacks against last level cache, or we haven't seen the prime probe attack against the last level cache. And the reason is that there are several challenges that prevent or makes this attack a bit more difficult. The first challenge is the last level cache is larger and slower than the L1. So doing a prime probe cycle on the last level cache is much slower. The second challenge is that we have difficulty of mapping our memory into the cache sets. The reasons for that, there are two reasons for that. First is virtual memory, as Gorka showed, hides information about the cache set index. And the other is that the current Intel architecture that divides the cache into slices, it uses an unpublished hash function. We don't know it. And the last challenge is the visibility of victim memory access. If the higher level caches do their job, then when victim memory accesses will mostly be served from the higher level caches and not from the last level cache. So even if we can monitor the last level cache, we will not see the victim access. So how we address these? To address the first challenge, we first probe only selected cache sets, not the whole cache at the time. For the for virtual memory, we use large pages, same as Gorka. I will not go over that in my talk because it will be really repeating Gorka's talk. And for the LLC slices, we empirically determine the mapping. We just probe the cache to find the mapping between memory to the cache slices. Intel, fortunately, takes care of the last problem. The last level cache in Intel is inclusive, so it means that it is a superset of what happens of the contents of the higher level caches. So if we evict data from the last level cache, that data is also evicted from the higher level caches, and any access to that data will be visible in the last level cache. So for the first problem, slow last level cache. We have some typical timing, access timing to the caches. This is Intel i5 processor. The L1 cache is 32 kilobytes. We can scan it in 2048 cycles. The last level cache is relatively small, 86 megabytes, and we need 3 million cycles to scan it. So we have 3 orders of magnitude difference in probe time. If we look at typical public key operations, they take several thousands to several tens of thousands cycles. So if our probe resolution is 3 million cycles, there is no chance that we will be able to distinguish between individual operations. So we can't work that way. On the other hand, probing a single set in the last level cache is still fast. And we demonstrated it by implementing a covert channel between VMs by programming two cache sets, and we get a bandwidth of 1.2 megabits per second, which is 6 times faster than the best known last level cache attack until now. Our solution to the size of cache is that we probe one or a few cache sets at a time, and instead of looking at the cache footprint that the victim leaves, we look at temporal access patterns over these few cache sets that we probe. Second issue was the large pages that we said I'm not going to talk about, so I'm moving directly to the last level cache slices. The problem is that the cache is the Intel last level cache designed with multiple slices. We have 1 slice per core. In this example, I have 2 slices, slice 1, which is gray, slice 0, white, and memory is mapped. The memory still maps to cache sets on these slices, but the decision on which slice it goes to is done based on some hash function that Intel does not publish. For the attack to be effective, we need to find memory lines that go to a specific slice, to the same cache set in a specific slice. So the way we do it is we build a pool of memory lines that exactly cover a single cache set over all the slices. And we do it iteratively. We start with an empty pool, and then we pick a candidate, try to see if we can add it to the pool without overflowing one of the slices. And to do it, we just probe it. So the way we do it, so for example, if we have this as the current pool, and we can see, hopefully we can see that it has 3 entries in slice 1 and 2 in slice 0, and we have some candidate. We access that candidate, and that brings it to the cache. And then we access all the memory lines in our buffer. And if the specific slice that this candidate is in is not full in the pool, then it will remain in the cache. On the other scenario, if you pick another candidate, it will go to slice 1, and when we access our pool, it will evict that candidate. So now we have 2 possibilities. Either the candidate remains in the cache or it is not in the cache, and we can distinguish between these 2 by measuring the time it takes us to access this candidate. If it is still in the cache, we can add it to the pool. If it is not in the cache, we know that we can't add it, and we go to and pick another candidate. When the pool is full, then we can partition it into slices. We can do it the same way. We just pick a candidate and see conflicts with the pool when we start removing elements from the pool. So we are able to create eviction sets for every cache set, for every cache slice. That leads to the attack strategy. What we do is we actually find these, and then we start searching these cache sets for temporal patterns that we expect from the victim. And the example that I'll show here is the use of the first example I'll show is how we find the square code when attacking square multiply exponentiation. This is an old version of GNU-PG. I'll show the later version of GNU-PG later. So the GNU-PG 1.4.13 uses square and multiply. We know that the algorithm does squaring, the exponentiation does squaring, then modular reduction, and then if the bit is set, it will also do a multiplication and modular reduction. So the behavior that we expect from the square line is that short burst of activity when we do the square. Then there will be some inactivity for the modular reduction. And if the bit is set, then the interval of inactivity in the square cache line will be a bit longer because it will need to do the multiply and reduce after square reduce. So in the diagram we have some example of probes of cache sets, and we see that some cache sets are not active. White is not active, black is active. We see that some cache sets are almost always active, and others show some sporadic access. And if we highlight one specific cache line there, the blue line, we can see that we have the activity that we expect from a square cache line. We have burst of activity separated by two sizes of intervals. And we can now start reading the data, or the exponent from this data. The first, we have square and modular reduction, and that's followed by another square, so we know that this bit was 0. And then we have the same pattern again, square and short interval, and 0. Then we have a large interval, so we probably had a multiplication in the middle, so the bit is 1, and we can continue, and we get the bits there. And if we do this over the whole exponentiation, we find the exponent, and that's the private key, and we've broken the encryption. When we move to a newer version of GNU-PG, GNU-PG 1.4.18 uses sliding window exponentiation. This was the current version when we did this attack. And the main differences from square and multiply is that to protect against the flash reload attack, GNU-PG changed the implementation of square. They don't use dedicated implementation. Instead, they multiply a number by itself. So it always uses multiplications. And instead of having just one value that it can multiply when it does multiplication, it pre-computes 8 values that are stored in a table, and it uses the right one when it needs. I'll not go into the details of how and why the sliding window works. That's just what we need to know about it. Now, this presents several new challenges. First is that the multiplier table is dynamically allocated. So not only we don't know which cache set each multiplier is in, this changes between exponentiations. So each exponentiation, the table will be in different memory location and different cache sets. The other problem is that memory multiplier use is sparse, irregular, and we actually don't know the access pattern, because if we knew the access pattern, we could have recovered the key to begin with. So we have a very weak signal there, and we don't know what the signal look like. And the last problem is that we cannot distinguish between squares and multiplications. So what do? First, we find the multiplication code. We know how to do that. It's the same as we found the square code in the previous attack. And if we look here, we find this code, and we see the access. That it will always be multiply, reduce, because there are no squares in between. So the access is very regular. And this doesn't give us any information about the key, because we knew it will be multiply separated by reduce. But what it does tell us, it tells us that at around time 50, the exponentiation started, because we didn't have any multiplication before that. And we can tell when each multiplication is taking place. So now the only thing that we need to do is find the multipliers. What we do know about the multipliers is that when we use the same key, the access pattern repeats across exponentiation. So if a specific multiplier is used in the third multiplication, it will always be used in the third multiplication. So we know that we have a temporal access pattern that we need to find. We don't know what the pattern is, but it exists. The way to find patterns that we don't know about what they are is we collect enough patterns, and then we cluster them, we'll search for similarities. So that's exactly what we do. We collect long traces that tell us both for both the multiplication line and some arbitrary cache sets. We want the multiplication set to know when multiplication takes place, and then we can see when when the other cache set is used during multiplication. So we collect this a huge number of these traces, and we run a clustering algorithm based on the added distance between them. And we get something like this. This is a single cluster. So we have each row is a trace of an exponentiation, and the horizontal line is the multiplications in this in the exponentiation, and the line is dark. The position is dark if in that exponentiation we saw activity in that cache set, in the cache set during the multiplication. And from here we can see that we have a pattern. We have each vertical line tells us that, and around that position we probably had multiplication. There are some errors in the attack, but we can filter them easily because they appear in one exponentiation, not in others. And we can compare this data to the ground truth. We have that ground truth, and we see that it really matches. We actually can say which of the multipliers this is because the multiplier is accessing the pre-computation when it is computed. It's a fixed position. So this allows us to find the multiplier. We look at all the clusters to find the 8 multipliers, and we can recover the whole key from that. In summary, we have cross-VM, cross-core synchronous attack on 2 implementations of exponentiation in 2 different versions of GNU-PG. The square and multiply, which has been used by Zhang et al., we attack in less than 1 minute compared to 6 hours that the attack took previously. This is still slower than flash reload attack, but unlike flash reload, we don't need duplication. We have the attack on the sliding window. This one takes much longer because we need to collect much more data. So we collect data for 12 minutes, then we do the clustering, and we need some more manual processing to fix the errors in the clustering. But we achieve full key recovery in a total of less than 25 minutes. This is something that was simply not feasible with flash reload because it uses data that is created dynamically. Flash reload needs the duplication. It doesn't happen without duplication. So to conclude, we have a practical side channel attack that on the last level cache. This attack is asynchronous. It is cross-core and cross-VM. We have a new attack strategy that we search for temporal patterns rather than looking for the special footprint that the victim leaves in the cache. We use large pages to find the mapping of memory lines to cache sets, and we have a new algorithm that maps these cache sets into or partition this set into slices without knowing the actual hash value. We implement a fast covert channel 6 times faster than previous covert channel in the last level cache, and we identified and helped fix a vulnerability in GNU-PG. Now, before I take questions, I would like to invite my joint first author, Fangfil Yu. She's a senior PhD student in Princeton. And with that, I'll thank you for your attention, and I'm happy to answer questions.
Go ahead.
In the interest of fairness, I'll ask you the same question I asked the last speaker. Which is what is the workload, and was there anything running besides the measurement and spice processes?
Okay, we didn't try to make things really quiet, but we didn't run anything but the 2 virtual machines. We do see some system noise, but we don't know whether the attack will work in presence of noise.
So I guess I have to repeat my previous question too then. Did you try it on Amazon?
I would like to answer give the same answer, but no, we haven't tried, and it's not only in that paper.
Okay. All right. Why don't we thank the speakers and the authors and.